So here we want to look at ramps, and in particular we're going to take a really cool guy on a ramp and we're going to go through a set of situations where we make a couple changes with adding a couple forces as we go. In our first case we're going to start on a frictionless ramp. And so here we have our object, and on the center of mass there's going to be a force of gravity down. And our really cool guy has a mass of 10 kilograms, no friction, and the ramp itself has an angle of 30 degrees. And so the only two forces in this case are going to be gravity straight down, and then there's the normal force perpendicular to the ramp. Now when we get into more forces, you can see the advantageous of this later. But when we deal with these forces, we need to be able to combine them to make a net force. And one of the best ways to do that is to rotate our reference frame. And so when we look at this ramp, what we want to do is we want to shift it so that it's flat. And what that'll do is that'll cause the normal force to be acting perpendicular to the ramp still. And from our perspective, it would be straight up. The problem with that is that our gravity is going to then act down. So what we want to do is we want to take this gravity and split it into two components. So this one vector is going to turn into these two. One is going to be along the ramp, down the ramp, and that's going to be what causes your motion. The other one is going to be perpendicular to the ramp, and that's going to be a force into the ramp itself, usually balanced by the normal force. So, in terms of mathematics, the component that is perpendicular to the ramp, gravity, is going to be the mass of the object times gravity, its weight, times the cosine of the angle of the ramp. And so the angle of the ramp is actually the complement of the angle of the gravity, and so the trigonometry dictates that this is switched from sine. And so here we have mg cosine theta, and that will be equal to the normal force in most cases. And then secondly, we have this other component parallel to the ramp. And that's going to be the weight again, but this time times the sine of the angle of the ramp. Okay. And in this particular case, that's going to be equal to our net force. And our net force is equal to mass times acceleration. And really, that's our net force along the ramp in this direction. The net force in the case of perpendicular to the ramp is 0, which is how we can conclude that these two values are equal to each other. So in this case, if we'd like to solve for what our acceleration is, we would take these two components of this equation, and the masses of them will cancel, and we can find that our acceleration will be equal to gravity times the sine of the angle of the ramp. So the mass of the object plays no role in this. And in this particular case, we would have 9.8 meters per second squared times the sine of 30. And so we would find that our acceleration is 4.9 meters per second squared. So a frictionless problem is pretty simple to solve. If we could look at this in a different way, it's going to be very helpful later on. Really what we're doing here is we're rotating this where here is your top of your ramp. Here is the bottom. And then we're splitting the gravity into two components. The force of gravity that's perpendicular to the ramp, which is going to act in conjunction with the normal force to give us a net force of 0, and the thing's going to fly off the ramp or go into it. And then there's also a portion of gravity that's parallel to the ramp, and that's what causes your motion. So our net force here, this is this mg sine theta. Now in the second portion, now we want to add in friction to this problem. mg sine theta. And then we're going to add to that the force of friction. And that's our net force in that direction. That's going to be equal to our mass times acceleration. Now, in order to figure out acceleration, we need to also know what the force of friction is. And our force of friction is going to be equal to our coefficient of friction times our normal force. So at this point, we can start plugging in some numbers. If we go back to the very top up here, our normal force is going to be equal to mg cosine theta, and that specific value turns out to be 84.87 newtons. Given us in the problem is our coefficient of friction, 0.100. So now we can find the force of friction from that. And then we can also plug in mg sine theta. So let's redo this equation here. Mass times acceleration is equal to our mass, 10, times 9.8, times the sine of the angle, and that comes up to be 49 newtons. And then we're going to add to that our force of friction. Our force of friction is going to be our normal force times mu, and mu is 0.1, so this is going to be 8.487. Now it'll be equal to our mass, 10 kilograms, times our acceleration. Now one more thing before you get beyond this point, you do need to account for the fact that the frictional force is acting up the ramp, the gravity force is going to be, the parallel component of the gravity force is acting down the ramp. Those are opposing forces, so one of these needs to be a negative. It's arbitrary which one you choose. If I choose the friction to be the negative direction, I can mark that here on my diagram. Down the ramp will be positive, up the ramp will be negative. Now I can add these two things together, divide the answer by 10, and I get acceleration equal to 4.13 meters per second squared down the ramp. And I can go back and compare that and say that makes sense because previously without friction I had 4.9 meters per second squared. Now that I add a little bit of friction into the equation, my acceleration is a little less than before. So that makes good sense. Now at this point we're going to add in a fourth force, and this is going to be an applied force, and we're still dealing with friction. And at this point things get a little tricky because really when you're dealing with friction you don't always have the total amount possible. So when you push on an object and there's a friction force resisting you, it resists exactly how much you push on it until you get to a certain capacity it no longer holds. At that point your motion is going to start. So sometimes we need to look and determine, are we at that point yet in this problem? So this time we're going to do with friction and with an applied force, same problem as before. So here's our ramp. Here's our really cool guy. We're going to have gravity acting downward. We'll have our normal force up. In this case, we're going to push up the ramp with 200 newtons of force. So we'll have an applied force there. And then we have a friction force as well, but at this point we really don't know if it's going to be down the ramp or up the ramp, or in some cases it can even balance. So I'm going to make a little note, there's force of friction somewhere, but I don't know where it is yet. So to look at that, I'm going to start going just like I had before. Now a lot of the calculations from this are the same, so we're still dealing with a 10 kilogram cool guy, still a 30-degree angle, and we're going to keep our coefficient to be 0.1. So if I look, the normal force hasn't changed from this. So if I start to look in my parallel direction, and I add up all of my forces in the parallel direction, I'll have an applied force up the ramp. I'm going to have a gravity component down the ramp, force of gravity parallel, and then I have the potential for some friction. So in order for me to really analyze what the friction is doing, I want to look at what these numbers are. Okay? So these are going to add up to the net force. They're going to be equal to my mass times acceleration. So my applied force is 200, given in the problem. The force of gravity parallel hasn't changed. It's still down the ramp. It's still mg sine theta. It's still 49 newtons. And then I add to that my force of friction. Now at this point, I can assign a negative to this. And I can look and I can see that my applied force is much larger than my gravitational force down, and so therefore the friction is going to oppose that force. So my friction is going to be a negative value, and since my normal force hasn't changed and my coefficient hasn't changed from the previous section, this friction force is still going to be the 8.487. Like that. And so now I can plug in 10 for my mass, combine these values together, and I solve for my acceleration. And that acceleration turns out to be 14.3 meters per second squared. Right, and that would be up the ramp, given my designation of positive. So now this thing will go up the ramp. Now, a word back on this. If we go back to this problem and we're looking at just the force applied and just this component of the gravity, the comparison of those two is what dictates what your frictional force will be. So if you have a case where the gravity is pulling by more than the applied force up, then your friction is going to need to oppose that net force down and will act in the upward direction. If, in this case, the applied force is much greater, gravity down was less, the friction will oppose that net force. So friction will tend to act against motion or against the net force. Now, there is a tweener case where anytime you get to the point where this force and this force are less than this amount apart, the friction will not act to its full capacity. So if we're only pushing, if we're pushing in this direction with 100 newtons, in this direction with 99 newtons, I would only have 1 newton of friction acting up. If I started to push down this way a little more, this friction would increase up to oppose that until it gets to the point where it's at this value. And at that point, you would see that the block, or the really cool guy, would start to move.